Okay, consider this. We have two coils at proximity of each other. The first one to the left, we call it primary coil. The second one, we call it secondary coil. As you might have noticed, the secondary coil is connected to a voltmeter. That will help us detect or measure any induced EMF in the secondary coil. The first coil is instead connected to a power source. In this particular case, that power source is labeled with the letters AC, and we see a sort of sine wave up there. What's that telling us is that we are powering it through an AC power source, an AC generator, which means that the current through that primary coil is going to look like this in time. A sort of a sine function as a function of time with amplitude or peak values and with a period or frequency, which means that the current through the primary coil is actually changing. Remembering that whenever we have a current through a coil, that coil is going to produce a magnetic field. Actually, whenever we have a current through a wire, that wire is going to produce a magnetic field. The magnetic field through a coil that looks like this, a solenoid, for simplicity, is given by this expression. B, in this case, since we are talking about primary, is going to be mu zero permeability of free space, kappa, which is going to be the permeability of the core of that particular solenoid, times n, and n sub p, let's call it, which is the number of loops per unit length. Remember, n sub p is actually the total number of loops in the solenoid over the length of the solenoid. I'm using the letter sub p here to tell us it's the primary, times the current in the primary. So the magnetic field produced in the primary is proportional to the current in the primary. If this current is going to change, that means that the magnetic field produced by the primary is going to be changing as well. Now, the fact that these two coils are at proximity of each other means that the secondary coil is going to experience the magnetic field produced by the primary coil. And since that magnetic field is changing, that means that the secondary coil is going to experience a change in magnetic field. If the secondary coil is experiencing a change in magnetic field, it means it's going to also experience a change in flux. Remember, the flux through the secondary, and I'm going to calculate it here for one loop, is given by the magnetic field that it experiences, which is in this case the magnetic field due to the primary, times the area through which we have that magnetic field, which is going to be the area of the secondary in this case. So since Vp is changing, the flux through the secondary is going to be changing, which in turn means we are going to have an induced current in the secondary according to Faraday's law. Okay. Let's calculate this. We said the magnetic field I need to change the color here. The magnetic field due to the primary coil is going to be given by mu0 kappa n primary times I of the primary, which means that the overall flux experienced by the secondary coil is going to be the number of coils in the secondary times the flux in each of the loops of the secondary, which is going to be NS BP AS. Remember, A is the area of the secondary, which is going to give us NS mu0 kappa NP IP and A sub S. The only quantity that's changing here is IP. So I'm going to isolate it of sorts. NS mu0 kappa NP IP. I need to take away that IP. AS and then IP. And all of this is a constant that we are going to call M. So my overall flux, NS phi S, is going to be that constant M times IP. Now, the EMF in the secondary coil is going to be minus NS delta phi in the secondary over delta T. So in this case, that's going to be, since the only thing that changes is the IP, that's going to be minus M delta IP over delta T. That constant M, I have to change the color in every screen. That constant M is what we call the mutual inductance between both coils. And as you noticed, in this case, it depends on the total number of loops in the solenoid in the secondary, number of loops per unit length in the primary, mu0 and kappa, and the area of the secondary. But all of that is not really, you don't need to remember that expression because it's going to depend on what kind of coils do we have. The key is we have what we call mutual inductance, and the EMF induced in the secondary is proportional to that mutual inductance constant and proportional to the change in current in the primary as a function of time.